So here is a summary of how to use the MATLAB code that comes with the text to plot direction fields and integral curves. So if you go to the class website under section 1.1, I provided a link to the code. So if you click on that, it'll take you to MATLAB's cloud service where you'll need to log in with your Loyola email address and password. So I can sign in. So you should be able to see an MA304 folder. So you can click on that and the code shows up in the folder. So I can double click on that and I have the option of opening it in MATLAB online. So let's do that. So this usually takes a second because everything is on the cloud. So depending on your connection, this might take a few seconds. So I want to make sure that I am in the current folder that contains the code. So the folder is MA304. So I'm going to double click on that. And now I can see the code inside the current folder. So this means that I can execute it by clicking this little green triangle here, as we did in class. But I'm going to show you another way of running this code. So we're not going to do anything with the text of the code itself, so we can close that file. And on the bottom left corner here, we can see this tab that says command window. Let's click on that. Now the command window comes up, and now we can interact with the code. So I'm going to type in the name of the file. So it's dirfields. So if I type that in, you can already see that MATLAB identifies it and it fills it in for you. So you can just click on that and hit enter. And now you are asked to enter the differential equation. The independent variable is t. The dependent variable is y. For the assignment, the first problem is the population model. The independent variable is also t, but the dependent variable is p. But we're going to replace p with y, right? So the differential equation is dp dt equals 0.4 p times 1 minus p over 100 minus h. Now we can type in the same equation with y playing the role of p, right? So this becomes 0.4, and in MATLAB, little star is multiplication times y times 1 minus y over 100. Then we can remove h. So I'm going to do the h equals 0 case, so I don't have to worry about that. So I mean, if I really wanted to, I can do minus 0 there. So that would take care of the definition of the differential equation. You can hit enter. I've asked you to plot it for t between 0 and 25. So the smallest value of t is 0. The largest value is 25. And in the y direction, the smallest value is 0. The largest value is 100. So at this point, what you should see is that the plot pops up on the right hand side. So I can resize the figure here, and now I can see the plot of the direction fields of the differential equation. But I want to add some integral curves to this. So I've asked you to add the plot of the population starting with a population of 5, 20, 60, 80, and 100. So we can add those integral curves to get a sense of how the solution behaves for various starting positions. So I'll hit yes for the solution curve. The initial time is 0. The initial value of y is 5. So the first solution pops up. I can continue yes, because I want to add more integral curves. The initial value is 0. Then the initial value of y is 20. And we can continue to 60. Yes, the initial value in this case is going to be 0. And then the initial y value is 60. So as you plot, you can see the integral curves pop up on the right hand side as we accumulate more solution curves. So the last one in this case would be 80. So in this case, yes, at 80, the initial value of t is 0. Then I can have a value of 80. Actually, there's one more at 100. So I'm going to do yes, 0, and the initial value is 100. So the 100 in this case is actually the equilibrium solution. So you see that at 100, we just get a horizontal solution. So we're done with the integral curves. I can plot, hit no, n, and then the code stops running. Now I want to save this. So if you hover at the top here, you see this little icon with an arrow pointing to the right. So if you hover on it, you get this floppy disk symbol. That's the save icon, so you can click on that. And now you have the option to save. So you're going to save in the MATLAB, in your MATLAB drive, essentially. So I've suggested saving this as a PDF. So let's call this plot1.pdf. So I'm going to select the MATLAB drive and then I can save. So now this has been saved. So if I click on my MATLAB drive, I can see plot1 there. So I can actually double click that and open this in a new tab. Now I'm just going to zoom out and I can see all the solutions that we've plotted. So there's a direction field for ODE, and then we can see the behavior of the population for different initial values. So we started 5, 20, 60, 80, and 100. So you're going to do this for different values of H, but you're going to repeat it for the same initial values of population, and then you're going to discuss the effect of H on the behavior of the population.